reactions, right? Was it? It was nuclear reaction. Nuclear reactions were basically of three types to when we classify them on the basis of their decayed elements. I mean, when they emit some elements or radiate some radiation, and on the basis of that, they are transferred from parent nuclei to the daughter nuclei, then we talk that nuclear equations are being formed. So I was saying that there are three types of decays: alpha decay, beta decay, and gamma decay. Alpha decay when alpha particle is emitted, beta decay when beta particle is emitted. So here I can say emission of alpha particle, then emission of beta particle, beta decay, and emission of gamma particle, gamma decay. So here, when alpha decay takes place, this is very genuine equation, and you people would be asked so many times from this topic that what happens when an alpha decay takes place. So during an alpha decay, there are 4 points you have to remember. 4 points. Please remember 4 points. What are those 4 points? That during an alpha decay, your element, which is your parent element, it is X, and its proton number is Z and mass number is A, right? And it is converted to a daughter nuclei Y. Its Z is decreased by 2 and A is decreased by 4. So please remember this thing, that along with we have an alpha particle 2He4, because that is a helium nucleus. So I'm going to write a simple notation over here, that during an alpha decay, two protons are decreased, our proton number is decreased by 2. Proton number, I mean Z, is decreased by 2. One thing, number of neutron, our neutron number is decreased by 2. Neutron number, which is n, it is not mentioned in this Z and A, is decreased by 2. I mean, two protons are released, two neutrons are released, and third, Z, which is sorry, A, which is its nucleon number. What is this A? Nucleon number. Please remember this all. Uh, I have to write in a sequence. Nucleon number, nucleon number, which was your A, that is decreased by 4. So please, if you will have these three information with you, alpha decay will never be a problem for you. Okay. Now come to this point. For example, uranium is there, and uranium is having Z. Its Z is 92, and A is 238. So if I say that an alpha is released from here, what will be its Z? It would be 92 minus 290, and 238 minus 4, it would be decreased by 4. So 4 would be less from here, it would become 234, and 2 will be less from here, that's why it becomes 90. Is it clear?
Yes.
Okay, so never forget this for your alpha decay. No more details or explanations are required for your alpha decay. So these three lines, that during an alpha decay, proton number is decreased by 2, neutron number is decreased by 2, and your nucleon number is something different, that is decreased by 4, right? Should I proceed to the next? During beta decay, I will write some properties of beta decay over here. Then we will come back to the point. During beta decay, you know what happens? Beta decay is a process in which a neutron is converted into a proton. This is the basic information. We have to keep this information with us. A neutron neutron is converted to to a proton. Okay, and beta decay is basically, beta means negative beta, or you can say -1 and 0, or it can also be written as -1 and 0 with electrons notation. So this is what the neutron number, one neutron, only one neutron. This one means you can write in words, one neutron is converted to a proton, or to one proton. So during this, if I consider this all in this way, that due to this, what happens? Proton number is increased by 1, proton number, which is Z, is increased by 1. Please remember this, increased by 1. Your neutron number, neutron number, which is your N, is decreased by 1. Okay, that is decreased by 1. And nucleon number, nucleon number, what is this nucleon number? Yes, yeah, yeah.
112.
A, which is
Yes.
A, which is basically N plus Z, is unchanged. Can you tell me why did I use this word that it would remain unchanged? If A is, N is decreased by 1 and Z is increased by 1, so overall there would be no change at all. You got it?
Yes.
Sure, everyone got it. I think Hassan, Ariba, and yeah, all of you. Are you people clear in this this statement, that what will happen
Yes.
during this all? Okay, now let's talk about that. There is an example of this beta decay. Carbon 6 and 14 undergoes a beta decay. Uh, Due to that, this 6 is its proton, Z proton number, and this is its A, it is 14. So 6 is converted to 7. It means 6 is increased by 1, and A has no change. Why? Because A is, its A was 6 plus 8, right? If I explain in detail, what was this? A A consists of protons and neutrons. So your protons were 6. It means how many neutrons would be there? Number of neutrons is A minus Z, na? 14 minus 6. So it would be 8. So in nitrogen, this is what, this is the carbon's nuclide notation, or carbon nucleons. Now, well, when I will talk about nitrogen, actually nitrogen has how many protons and how many neutrons?
7 proton.
Again, I
And
can write protons plus neutrons. So number of protons are over here. So nitrogen has 7 protons. So if its nucleon number is 14 without chain, so how many neutrons must be there? Must they be equal to 7 or not? So did you notice that P is increased by 1 and N is decreased by 1? That is what I have written over here. Okay, is it clear? Should I
okay.
move to the next slide? Any question till now?
No, no question.
Okay, then during gamma radiations nothing happens. Why? Because during gamma radiations, just a sort of energy level is decreased, so excitation, excited state, sorry, that nucleus um, decreases its energy, so it comes to the metastable state, right? After undergoing a gamma decay, its energy is decreased, so it becomes not exactly the stable state, but it is the metastable state, or you can say semi stable state. So This is basically the gamma radiations. So here, the problem solving. Yes, I will just do a few ones, not all. Right? Fill in the gaps in the following radioactive decay equations. Oh, yes. Electron is -1, so you have to write first noun things. Okay. So H goes to helium, hydrogen goes to helium with an electron is emitted out, beta particle is emitted out. So what should I write over here? With H के Z की जगह क्या लिखूंगा हसान? What should I write to this Z? I told you that all the Z's on left hand side should be equal to the Z's of right hand side. Why did you not notice that all? That over left hand side and right hand side Z should be same. Then I told you that all A's of left hand side must be equals to all A's of right hand side. So please, according to that, just help me out to solve these equations. So what about first equation? Who will solve it? वो light off करके.
Okay, first one.
Yes, first one. Okay, yeah, try it. Try first one. It was
So,
-1.
yes, -1 and
So let's say it is X. Let me help you out for first one. So all of you should take care of these equations. So X is equals to 2 minus 1, which means X is equals to 1. So just write 1 over here. Okay. Then for its A's, when I solve for A, this was for Z. And if I solve for A, 3 should be equals to X plus 0. X plus 0. It means X should be equal to 3. So I have to write 3 over here. Now check this one out. 2 minus 1, 1 on the right hand side and 1 on the left hand side, same. 3 plus 0, 3, and 3, they are same. So is this clear to you?
yes,
Okay. Now, Hassan will solve equation number 2, and Ariba will solve equation number 4, and Yahya will solve equation number 6. You have 1 minute each. Yes, yeah.
yeah. The sixth one.
You were for 2 or 6?
Okay.
No. You were for 6?
Yeah, I guess.
Yes. You were for 6.
Okay
You
then.
can name it
Um,
simply X, no problem. If you do not know the name of this
yes,
nuclei, it does not matter.
so let's say um 28. So there will be 28 nuclear number,
Okay, 28, yes.
and
Then what about this beta?
beta will have 0 and -1.
Okay. So what about the Z of X?
Um, plus, plus one. Yes.
Yes, because we are not having anything over here. So if we write half of the usually aluminum is 13, mostly it is 1328, right? So if you have this 13 over here, so it would be what? 14 over here.
Yeah, but
Got it?
13 isn't written here. How do you know that? Do we
Sorry?
have to memorize? Do we have to memorize that? Sir?
No. It is almost this one. This is what? This is A. So usually, A is Z plus N. So most of the cases, Z and N are almost same. Got it?
Yes.
Yes. Or if they would not be same, N appears either greater or equal to Z. This is the situation all the times.
Okay.
Okay. So is this clear? Yes, Hassan. Next is your turn. Will you explain your option? Meanwhile, Yahya, you can try any one or two more by your choice.
Okay.
Hassan, बताओ बेटा. Hassan. Okay, अरीबा आप बताएं.
Sir, question 4, am I right?
Yes.
Honestly, I don't know how to do most of it, but I do know that for BI,
Okay,
the
BI whatever. This is Bismuth actually, but no problem. We are not supposed to memorize their names, but that is Bismuth.
so sorry, sir.
Okay,
Um,
no problem.
is even though it's gaining one proton, the nucleon number is gonna stay the same. So 209 is automatically gonna go over there as well. I'm quite sure.
Good, very good.
Now
Okay,
I don't know what goes in the question mark, but because usually lead is a part of uranium, so now I'm confused. It's gonna be
no
like
problem. No, it is an electron. It is an electron meaning beta particle.
E0,
So it
right?
would be -1 and 0. Yes.
Okay.
Or you can simply write -1 and 0. Okay,
Okay.
good, good. And yes, uh, हसान बेटा आप बताइए सबसे आसान आपको दिया था.
सर मेरा नेट चला गया था अभी बताएं कौन सा पार्ट
Part 2. Yes, Ariba, you can try 5 1 fifth. Sorry, 5 6 or yes, whatever you want. It's now your choice. Yes, हसान बताएं बेटा जी कैसे ये आप सॉल्व कर लोगे. Yes.
Whose turn it is?
Sorry. Yeah.
Whose turn it is right now?
Hassan's turn. Yes, you
Okay.
can answer if Hassan. You want to help Hassan. Yes. The friends
Um,
in need is friend indeed. So
सर ये आरए पे 229 आएगा या
okay. RA पे 229. Okay, देखो
या x इज इक्वल टू 4 1 229
4 221 229 -4.
-4
So 2 2 5. ठीक है. So if I give you that this thorium has 90 these protons, so what would be the radon's number?
88
88. Very good. You all are passed. Maze karo. Enjoy the life. Now, come to next topic. Oh, there are so many problems here. I will send you these all for your practice. Okay, now we will talk about some other nuclear reactions. These are actually called nuclear processes of fission and fusion, right? So, simply speaking, that there are two main processes in which a nuclear reaction takes place. One is fission, right? Fission is splitting into small, right? Splitting into smalls. This is just a perception of that. And then fusion is merging into large. When we have very large nuclei, they performs fusion, right? So for large nuclei or for heavy nuclei, fusion is fusion takes place, and for small nuclei, fusion takes place. So just go through the topic. Nuclear reaction. Nuclear fission is the process by which multiple atomic nuclei join together. This is a fusion, right? To form a heavy nucleus. It is accompanied by a release or absorption of energy. So simply speaking, nuclear fission is the combination of the process in which small nuclei together form a heavy nuclei. So that process takes place in the stars. Oh, sorry, the nuclear okay, in this slide, the next statement is for fusion, so I have explained it. I hope that it would be clear to you. So in fusion process, in nuclear physics, it is very in which a nucleus of an atom splits into two or more small nuclei as a fission products, and usually some byproduct particles, right? So I believe that this is not hard task to remember, as I have mentioned this. Splitting up fission and fusion means fusion itself is very good topic, good point. Fuse together, merge together, or simply you can say fuse together. Okay, fuse together. Thank you. Now, a nuclear reactor. Okay, wait. This process describe with the idea of the block diagram by which type of fission takes place in reaction and power station. So this is nuclear reactors mechanism, and actually in nuclear reactor, what happens? Fission happens. Okay, so I'm gonna explain fission over here. Nuclear reactor is basically a setup over there where we perform the nuclear reaction. So basically their uranium is used as a nuclear fuel, and that is um, used to provide heat energy, and that heat energy is basically used to boil the water to make the steam, and then that drives the turbine and generator. This is a perfect description of a nuclear power reactor as a whole. That what happens during splitting of uranium, heat energy is produced, and that heat is used to boil the water, and that boiling water is used to produce the steam, and that steam is used to run the turbine generator, and electricity is generated. This all is in bombs. This is basically what happens in nuclear bomb. Okay, the in nuclear bomb we don't need controlled reaction, but sorry, I had to tell you that here we perform controlled reaction. Okay, what do we do here? The reaction is controlled. Okay, so control reaction, we use some of the nuclei out of here. I will explain that what happens in the nuclear reactor and how do we control these all nuclei. So in chain reaction, the reactor core, there are some sort of nuclei which splits up, producing a lot of heat and continuous process that is called chain reaction. Here is that chain reaction. That chain reaction is a slow neutron is bombarded on the uranium, and that uranium is split it up into two fission products and three neutrons. This is very important. Now these three neutrons hit three other uraniums. Those three uraniums are again basically converted into three sorry, each of them is converted into two byproducts and three neutrons. It means now it is possibility of nine uraniums to be broken, right? In this way this process continues, and in seconds, I mean, trillions of uranium atoms have been decayed or have been broken. So this makes the nuclear fission, mean horrible, because it releases energy, but it means that energy should take some time to be released. But this energy which is being released during this fission, it happens in just seconds, right? So we have to control it. That is controlled by the moderators. By using graphite rods we can control these reactions, and controlling means we block uh, two of the neutrons and we let one neutron, and that neutron continues or take part in the further reaction. Okay, here this is the uh, here is the nuclear reactor diagram, right? What happens, this is the fuel elements, I mean the uranium rods. Uranium is not just sprayed over there, it is placed in the form of rods. Then steel pressure vessel, because a huge pressure is over there. If you see a season of Chernobyl, that is a documentary actually. Did you ever see that, any one of you? there
No,
was a
sir.
there was a nuclear reactor in Russia, and that was exploded. Some people say that this was
Chernobyl?
Chernobyl. Chernobyl is basically yes, it is name of that was the name of the reactor, I think, or name of the city. I
No,
don't know, but it
the
is
town, the district in the town.
yes. Was it now?
Yes, it was name of the district.
Yes. So that reactor was destroyed. It is said that some American conspiracies, due to some American conspiracies, but we do not have any authentic
It's just
mean.
rushed project.
Yes. So that was a Cold War time between Russia and America, so anything can happen in that war time. So this was due to, I watched that properly, I mean with the physics of sorry, eye of physics. There was a huge pressure developed in this steel tank, I mean steel compartment, because the pressure chamber, there was a technology to release the pressure with respect to time. So there were some people who did not manage that pressure, and that all happened. It is very informative when you are going to have a good knowledge about the nuclear reaction or nuclear physics. It is just, I think, two episodes or three episodes, probably, because
सर सर
I
6 है कि 7 एपिसोड हैं?
6 7 episodes हैं.
जी
Good. So it, after your exams, um, you have to watch it, but not during exam. अभी आप लोगों के पास time, हाँ weekend पे कर सकते हो when you have your chill time. It's not so big. Okay, so
Actually,
let's talk.
I'm having my winter vacation right now. I'll watch it. Why not?
Yes, yes, you can because you have a lot of time. But these two guys have to appear right now.
Oh, yeah.
That's why you have a lot of time. You can see that. You
Best
can
of
watch
luck
it
for you
in
both.
detail. Yes. So fuel produces heat, which is used to boil the water to make the steam. Here is that all block diagram. Uh, yes, actually, I was explaining right from here. It is a closed container, which is, I mean, a self-sustained system in which a water is taken in from one side. From here, hot water and cold water is split it up. Check this one out. uh, Due to heat, reaction is taking place over here, and due to that, what happens, a huge amount of heat is being produced. Here you are having control rods, and when we lower these control rods, right, what I was talking about over here, that you can use rod to block these neutrons. So here those rods are basically placed in this way. So these rods are lowered, these control rods, usually they are made up of graphite or cadmium, and they reduce the rate of reaction. And when they reduce the rate of reaction, low energy or smaller energy is produced. So what happens, it produces a lot of heat. This all is steam. Check this one, the arrows shows that this all is a very huge, I mean, temperature over here. So the water which is taken in from here, it is pumped to this over here, right? When water is pumped into, actually that water is used as a coolant, as well as this water is then pumped out. It is automatically pumped out, because when it becomes steam, we provide an output or outlet to the stream, and then it is a pressurizer, I think so, yes. So it may be it may condense that steam to somehow. I'm not quite sure about the function of the pressurizer, but usually it seems that it would condense that, and then that water is again sent to the boiler, and these boilers are maybe it would produce low pressure, or it would control the pressure of the steam. And from here we are having some sort of boiler. It is called boiler or steam generator, and then that steam is provided to the turbines, and those turbines are used to run the generator. Right, we have studied in alternating current generator is a device which produces electricity, and so on. In this way, electricity is being produced by this huge and mega event in nuclear reactors, right? So in star formation, fusion reaction takes place. No fusion at all in all over the stars. Okay, let me tell you one other fact as well. You know, there are so many countries which are claiming that they are having hydrogen bombs. There are almost seven, I believe. I'm not quite sure that whether some new addition is there, but they are seven. Okay, so what do they claim? That they have prepared hydrogen bombs. But remember this thing, hydrogen bomb is based on fusion process, right? And that nuclear bomb, what we call nuclear bomb, that is a uranium or a polonium bomb, that is based on fusion process, right? So usually we have uranium bombs, but not the hydrogen bombs. I mean, I believe this thing. I don't know that it is true or not, but sometimes, you know,
Hydrogen bombs also use fission. They have small
yes.
fission bomb
Mhm.
that create pressure on the hydrogen, and hydrogen starts fusion for like
Yes.
split second.
So exactly. So this was what I wanted to explain. That actually in the hydrogen bombs, our hydrogen is used in fusion reaction. So when we have the hydrogen bombs, we must have, or when we have to produce the fusion, we must have to produce a temperature of almost 25 million Kelvin. Can you believe this thing? That whatever the temperature is, that million. This is almost right. Some of the temperatures, some of the reactions started at lower temperature as well. But this is the ideal temperature for your fusion reaction. Now, what happens? We have a console of fusion, right? And in that we have a hydrogen fuel inside. So First, we perform fission in the outer casing, and then that outer casing produces a huge temperature and very high pressure, because that inner casing is also in mean is a console. So at that time, hydrogen fuel burns out, I mean fusion takes place. So inner core is using fusion. So two reaction takes place, or two nuclear processes take place at a time. That's why this hydrogen bomb or this technology is mean so severely dangerous. I say that uh, we have to mean we have to just avoid these type of you know inventions, so that if they would not be in the controlled mechanism, if they will not be in the some wise people's hands, they would be very massive destruction would take place. So let's have a just overview of that. In stars are the most widely recognized astronomical objects, and they represent most of the fundamental building block of the galaxies. And stars, when they enough dust and gas clump together because of the gravitational forces, the gravity pulls the dust, because this is the why I'm going to go through this slide, because that is also the part of your star formation. So the gravity pulls the dust and gas particle together. As the gravity comes together, it gets hot, and the star forms when it is hot enough for the nuclear reaction to be started. That is the point when, which is called your main sequence of the star. At that time, star is basically star burns out. I mean, light, our sun is now uh, burning its hydrogen. After some time, I mean, not some time, after some million years, it would burn its helium, and so on and so on. So this releases the energy and keeps the star hot. It means keeps the star live. So the star energy source is the sun, and other stars use nuclear fusion. This is the more favorite MCQ of the examiner, that um, how the energy is being formed in the star. So it is being formed by the fusion process, right? During most of the uh, stars lifetime, the hydrogen nuclei fuse together to form a helium nuclei. As I told you that, oh, check this one out. It is 1 2 3 4, it is 15 million degrees centigrade. Check this one, right? So the temperature required is in millions of degrees. That's why they fuse together. Actually, fusion means, if you give me just um, small time, little time to make you clear, these are the hydrogens are protons. You know, when protons are brought closer to each other, they repel each other. So they never at- interact with each other at normal conditions. When you will bring them closer, what will happen? They will be repelled, just like your springs. So if we provide them so much energy, that when they are bombarded on each other, when they collide with each other, they basically rupture, one proton rupture the other. I don't know how to draw that, but they basically merge together. That is the state when repulsive forces are overcome by your attractive, I mean kinetic energy. That is the only way to make our protons to be fused. Okay, so these are some sort of exam questions. Penetration and all that stuff is there. I will not go through these, because it would be some sort of waste of time for me, because I have to complete this topic today, inshallah. I will try my best. Okay, now let's talk about half life. This is the last part of your, probably not the last part, because I have to talk about the hazards and safety precautions of these nuclear tracers. Okay, so when we talk about half life, Half life means the time in which half of the nuclei are gone, right? The time in which half of the nuclei are decayed. Is it clear? So, the time in which half of nuclei are decayed. You can write in this way. Or in other words, the time in which half of the nuclei are left behind. Oh, sorry, it is written, so why I'm going to waste that? The time in which the time taken for the radioactive nuclei to be decayed to its half, or it is also defined as the time taken for the count rate to fall to half of its original number. So here it is what it is very important thing to remember from here. It is very important diagram rather. Check the brown ones. They are decreasing to its half, but original number is not being changed. Is it changed? Total number is total number changed? There is a pile of atoms or nuclei in front diagram. The pile is same in the second, same in the third. But what change do you observe? Yes,
Yes. What?
the number of browns are decreased to half in this diagram, and then they decrease to half in this diagram.
Are
So
browns the undecayed ones?
yes, they are
Okay.
16. Here they are 8. Here they are 4. The brown ones, right? So they are basically brown color is the color of uranium mostly. So brown ones they are parent nuclei, right? So originally whatever the number of purple are there, because we cannot count them right now, so that has been increased by 8 and then they had to increase by 12. So the number in which half of the nuclei have been decayed, that is called your half life. So let's say there are two techniques for half life. For example, one is the graph technique. Okay, I will tell you how to calculate that. First I will let you know the calculations of half life, because so many questions are asked from this topic. Calculations in half life. In half life. So what calculations we do in the half life? They are, first, let's say, I have to select any other color, probably this one. Yes, for example, let's say I have 160 nuclei, or undecayed nuclei. Undecayed nuclei. Okay, and they decreased to 80, right? In how much time? In 2 hours. If in 2 hours they decrease to 80, so it means what is their half-life time? Half-life time is 2 hours. Okay, in next 2 hours they would be decreased to its half, which is at the current half. They would become 40. And how much time would be then spent? In 4 hours, I mean two half lives, two times their half, then they would be decreased to 20. And how much time do you expect? In 6 hours. In 6 hours, it means this is your third half life. Are you people getting it? Okay, now
Yes.
in this way it would be decrease and decrease and decrease. So let's say, let's make it final. 40, and 40 will be in in how many hours? In 8 hours. Or how much hours? In 8 hours. So this is its fourth half life, right? What is it? This is fourth half life. Now, my question is, did you notice down that 160 is 160 become 160 divided by 2 after first half life, then 160 divided by 4 in second half life or after second half life, 160 divided by 8 in third half life, and 160 divided by 16 in fourth half life. Did you notice down? Okay, I mean 80 is 80 is what? 80 is 160 divided by 2, na? What is 40? 160 divided by 4. What is 20? 160 divided by 8. And what about 40? 160 divided by, hello, are you there? Yes.
Yes, sir.
So for all the times your number is decreasing to its pre-existing half, pre-existing half, pre-existing half. So this is what, how do we perform calculation? How do we perform calculation? It means after first half life, I will write some values over here. Yes. Do you have any confusion?
So will it eventually reach zero or
No, no, no. We will not reach to zero. Zero, reaching zero mean we can consider that it would take infinite time. But usually the graph does not touch the axis. Usually it happens. Now, if I have an equation for you, for example, n naught is original number of nuclei, right? Original number of nuclei. So here, what is n naught? Which is your 80. Okay, n naught is original number of nuclei. Then n is remaining number of nuclei. Remaining number of nuclei. So if I say that n will be n naught divided by 2 after first half life, one half life, n will be n naught divided by 4 after second half life, n will be n naught divided by 8 after third half life, and so on. So do you think that n will be basically n naught divided by some numbers power n? Because here if I want to write this, it is 2 power 2, it is 2 power 3. So this 3 is this 2 is this. So if I have n is equals to 2 power n after how many half lives? After n half lives. For example, 6 half lives, so it would become n to n power 6. This is where n is number of half lives. What is n? Number of half lives. Number of half lives. Now check this one. Check the graph. That is one way. Calculations from the graph is one way. So if I have 800 number of nuclei, then these 800 would be decreased to, sorry, 80. Sorry. If they are 80, then 80 is decreasing to 40 in 2 minutes, right? It means its first half life is 2 minutes. Then 40 is decreasing to 20 at this point. It means this is its second half life, which is 4 minus 2, 2 minutes, right? Are you getting it? Then so on. If you move on, this sample is getting half, or its half life is 2 minutes. What is its half life? 2 minutes, and so on. So this is basically from the graph. And if you don't have the graph concept, then you can have some calculations over there. Let's say, yes, over here, if I say that you have 1600 nuclei, how many nuclei do you have? 1600 nuclei, and these number of nuclei are um, are undecayed, right? They are undecayed nuclei. Now, my question is, if the sample reduces to 4 in 40 minutes, 40 minutes, calculate its half life. Calculate its half life. Okay? Are you people getting the question? Ariba, how much time do you have?
About 8 minutes, sir.
About 8 minutes or 1 minute?
I would say 8 minutes.
Okay, okay, okay. I will free you then. Don't worry. So 1600 nuclei are there, and sample reduces to 4. So it means, let's make it small, because you are not having time. So let's make it 160, and let's make it 40. So 160 is decreased by 2, and it becomes 80. Then 80 is decrease, sorry, is it become half, so it become 40. And how much time did it take? 40 minutes. It means this is happening twice in 40 minutes. So 2 times in 40 minute means 1 time in 20 minutes. Are you getting this logical explanation? That
Yes.
if it is reduced, or if it had been decayed 2 times in 40 minutes, it means one decay had happened in 20 minutes. So its half life is 20 minutes, right? So there are some other calculations as well from the half life. I would uh, basically explain all of that with another aspect, which is background radiations. Nowadays examiners favorite hot favorite topic is correction of background radiations. Okay, correction of background radiation. So I will let you know about that in my next lesson. Got it? Are you people agreed with this all?
Yes.
Okay,
Yes,
see
sir.
you inshallah. If you have any question, then let me know. And one more thing, I had planned classes for you at the weekend, but at this weekend, I would not be available over there. In the previous weekends, you people were not there, but at this weekend, I will not be there. So, हिसाब बराबर ठीक है